We're going to start this section with sort of a thought problem. So let me kind of read the situation to you, or you can read along with me, and then let's sort of have a think out as far as how we might go about figuring this question out. We've got two bands that are going to march in a parade. One band only has 24 people, and another band has 30. We want to make them separate from each other, but here's the catch. We want to make sure that when they're marching, they have the same number of columns. So each column needs to be the same size. What's the greatest number of columns that they can have march in this particular parade? Okay, so you have to kind of think about how would we do this? We've got two different sized groups, but we want to separate them into equal pieces, essentially. So if you kind of think with the 24 member band, how many different ways could I split them up? Well, I could do one person in 24 columns. I could do two people and have 12 columns. I could have three and have 8 columns. I could have 4 and have 6 columns, right? But the only different ways that I could stack them up. With the 30 member band, could do 1 and 30, could do 2 and 15, 3 and 10. See, 4 does not go in there, 5 does, 5 and 6. Okay, and so where do I see number sets that they have in common? Let's see, so I can see there's a 1. They both have a 1, that's kind of boring. They both have a 2, they both have 3s, and they both have, looks like 6s. So how would, kind of brings up what concept are we trying to work in and talk about here? So before we'll come back and answer this question, but let's get some definitions under our belt first. Okay, so before we can fully address this question, we need to get some terminology and definitions into us. So let's take a look at some ideas, and then as we get a little more knowledge, we'll come back and revisit the question and see if we can answer it a little bit better. All right, the blank or the blank. Okay, the greatest common divisor or affectionately called GCD, or another name is called greatest common factor. And the nickname for that is GCF. All right, so the GCD, greatest common divisor, greatest common factor of two numbers, A and B but not 0, is the greatest number that divides both A and B. So it's the biggest number that happens to go into both numbers. Let me back up. So going back to this list of common factors, what was the biggest number in the list? Okay, and it was 6. It went both. So we would say that the GCD of 24 and 30 is 6. The greatest common divisor of both those numbers happens to be 6. Okay, so now we're going to take a look at some different methods and how to determine the greatest common divisor. First idea we're going to look at is something more concrete, something you can hand students and let them sort of see for themselves how this works. So let's say I've got a rod of length 6 and a rod of length 8. That just simply means that there are 6 smaller segments that I could break this up into. Gotta love my 3D skills there. And then there's another 8 that I could break that up into for the 8 rod. Okay, so if I want to literally break it up into smaller pieces, I could have one rod of unit length 6, or I could have, one rod of unit length 6, or I could break it up into 6 unit 1 length. So in other words, like this again. So I could have 1 of unit of length 6, or I could have 6 of unit 1. I could have 2 of unit 3, or 3 of unit length 2. And then with 8, I could have one rod that's 8 long, or 8 small tiny rods that are 1 unit long, 2 rods that are length 4, or 4 rods that are length 2. Okay, and as we start partnering these up, notice, okay, the biggest number that goes into both of them happens to be 2, and we can literally just put the rods on top of each other and see that yes, you can get the same, you can get the length, you can rewrite the lengths in terms of the other length rods. So we can physically see that the GCD of these two numbers, so GCD of 6 and 8 happens to be 2. Okay, it's called the colored rod method. The intersection of sets. So let me give us 2 numbers here. Let's take 20 and let's take 32. Okay. And what I'm going to do is I'm going to make a list of all the factors of 20. So 1 and 20, 2 and 10, 4 and 5, and then I'll make a list of all the factors of 32. So 1 and 32, 2 and 16, let's see, 3 does not go in, 4 does, so 4 and 8, 5 doesn't, we're good, so we got them all. And once I got up to 8, then I know I've got all the pairs. Okay, so with the intersection of sets method, I just kind of look and see what numbers do they have in common. They both have a 1, they both have a, I'm sorry, highlighted the 2 there. I wanted the other 2. They both have a 2 in common. They both have a 4 in common. So what's the biggest of that set of common numbers? And that would be 4. So the GCD of 20 and 32 happens to be 4. Okay, so the prime factorization method is going to have a kind of similar feel to the set method. It's not really. Let me give 2 numbers here and kind of highlight how this works. So prime factorization is great if we have a number that's got a lot of pairs in it, because instead of thinking of, well, let's see, 1 and 180, 2 and 90, 3 and, instead of coming up with these different combinations, instead I'm going to break it up into its prime factors. And so we can do 2, well, let's start with the smallest number, so 2 and 90. 2 and, let's see, 90 breaks up into 2 and 45. 45 breaks up into 3 and 15. 15 breaks up into 3 and 5. And now I've got all of the prime numbers that break up that number. So 180 would be 2 squared, well, yeah, 2 squared times 3 squared. Well, change my mind again. Let me write that out. So 2 times 2 times 3 times 3 times 5. Okay. 168, I'm going to do that same factor tree on. I know 2 and 84 goes into that, and 2 and 42, and 2 and 21, and 3 and 7. So I can see that I have 1, 2, 3 2s, a 3, and a 7. Okay, so what I'm going to do, and this is where it kind of has a similar feel to the set method, I'm going to look for what they have in both sets. So I can see they both have a 2, they both have a 2, and they both have a 3, right? And that's about it. That's all they have in common. Okay, so the GCD for 168 and 180 is going to look like 2 times 2 times 3, and then I just have to multiply that out. So 2 times 2 times 3 would be 12. So the greatest common divisor of those two numbers would be 12. All right, so that brings us to another definition called relatively prime. Um, Let me start with just a general idea as to what this refers to. If I take any two numbers, it doesn't necessarily mean they are prime, but any numbers, let's take something like 6 and, well, not 6 and 14, 6 and 25. Okay, something like that. The factors of 6 are, well, we got 1, 6, and 2, and 3. And the factors of 25 would be 1, 25, and then 5, right? Okay, what do they have anything in common? They don't. Notice that the only factor they share is the 1, and so they don't. So as far as they're concerned, they're prime to each other. They're relatively prime. Okay. So the definition of what relatively prime is if I have two whole numbers where they're both greater than 0 and a greater than or equal to b, meaning clearly one is bigger than the other, or at least they're the same, then the greatest common divisor of those two numbers is the same as the greatest common divisor of this r and the second number. The second number being the smaller of the two. R we define as the remainder of when we divide a by b. Okay, so what this means is we're going to take two numbers, we're going to divide, look at the remainder, and the greatest common divisor of the remainder of the second number is the same, would be the same as the greatest common divisor of the original two numbers. Okay, so this particular process is called the Euclidean algorithm. Euclidean algorithm. Okay, so let me kind of go back to my two numbers here, and so you can kind of see on a very simple sense what it's talking about. Okay, so I want to go back to the 6 and 25 and show how this idea of Euclidean algorithm applies to just these simple numbers, and then we'll look at some more challenging examples. Okay, so let me start with, let's make sure the conditions are set up. So if 6 and 25 are any whole numbers greater than 0, okay, they both are, with a greater than or equal to b. All right, so I'm going to set up a to be 25 greater than or equal to 6. Then the GCD of 25 and 6 is going to equal the GCD of the remainder and 6, so I need the remainder. So 6 goes into 25 4 times with a remainder of 1. Okay, so that's what's going to go there. And then I'm going to take 1 and have it go into 6. It goes in there 6 times. Sorry. So we get a remainder of 0. So I can say that that's the same as the GCD between 0 and 1. And so that would make, or we keep going until we get that remainder of 0, and that would make these two numbers relatively prime to each other. And so, okay, so since the last divisor was 1, that makes the greatest common divisor of 1 for all of these things. And then this is what we call relatively prime.